welcome to our video today where we're talking about Gen Chem chapter 10, acids and bases. So before we start this video, I just want to give a little bit of a disclaimer. So acids and bases has a lot of different content that can be included. So I know that I have said this with some of my other videos, but just like please listen when I say this with this one. Use this as your mental checklist. Say, okay, yes, I remember this equation, I remember this concept, yes, okay, I've got it. Or, I haven't heard about that, or I don't know what that means. Let me go look and kind of do some more research on this topic that I don't know and I'm not comfortable with. And I say that because there's going to be some things I mention here to direct you to different resources that will better be able to help you, just because there's like so many details. It would take me 10 boards and 10 days to like go through all the different problem types, examples, this, that. So it's really up to you to like use this and just say, okay, like I get this concept, let me go look for practice problems that I can use this and apply it. Or, okay, yeah, I got this equation, I got it down, let me put it on my flashcard. Okay, now how do I use it? Okay, she said go to this website for this. Okay, let me go do that. So kind of use this video in that way, just because I didn't really have time to do examples, and that is really how we're going to apply a lot of what we're studying, but definitely these contents that we're going to talk about. So yeah, just use this as your surface level, okay? And also, let me just say, I've probably watched every single video there is on YouTube about acids and bases. So don't be afraid if you don't understand this stuff right away, and if it takes you a while to grasp some of the concepts, because this was definitely one of the more challenging ones for me. So let's get started. The stuff in the green is good, you can understand and memorize. When we start getting into the purple and the red, that's when you should, just take it with a grain of salt and then keep studying. Alright, so let's start with our definitions of acids and bases. Because as you know, just like for, when we gave a definition of redox reactions, Leo the Lion says Gur, we've talked about how acids and bases can do different things. Oxidation and reduction are different things. They're related to hydrogen, related to oxygen. It doesn't mean one specific way that these substances act. So it's the same thing for acids and bases. I just want you to recognize that they can act in a couple of different ways that make them an acid or a base. So first thing is our Arrhenius definition. An acid will produce H plus in solution, or a base, I know you can't see this for some reason, the light is really hitting it, but it says produce OH minus in solution. Okay, that's for an Arrhenius base. We have a Bronsted-Lowry definition, which is where it states that acids donate hydrogens and bases accept hydrogens. So the Bronsted-Lowry definition is related to hydrogens. Then we have Lewis acids or Lewis bases. Lewis acids accept electrons. They are electrophiles. Where bases, oh my goodness, I said that for both of them. Except this one is going to be donate. I'm going to change that really quickly. Okay. So, Lewis acid accepts electrons. It's an electrophile. Where Lewis base donates electrons, making it a nucleophile. Okay. And we can also have amphoteric species, which can act as when a substance can act as an acid or a base. So water, H2O, is a great example of that. And then this is just like the general equation that we're looking at. So when we're looking at the acid-base reaction, you have an acid is going to produce a conjugate base, and the base is going to produce a conjugate acid. So these terms are important, and we're going to talk about them a little bit later. But one thing that is also super important is knowing your strong bases and your strong acids. So the strong acid list is a little easier to memorize. There are 7. So you have HCl, H2SO4, HBr, HI, HNO3, HClO4, and HClO3. Those are the 7 that you would kind of memorize for the MCAT, and you should definitely recognize as being strong acids. Whereas strong bases, for example, NaOH, KOH, you can also have like different variations. So basically anything that has an OH minus in it, like in solution, like we said. So bases are a little more tricky, but if you see the OH, you can be pretty confident with that. The thing about strong acids and strong bases is that they will produce, let me click here so you can see, they will produce, or they will have inert conjugates. So if I have a strong acid, this conjugate base is going to be inert. It's so weak. It's such a weak base. Whereas if you have a strong base, its conjugate acid is inert. It's very weak. Okay? When we say strong, we mean that it dissociates completely. Okay? So if we have HCl in solution, HCl will dissociate. You'll get H plus and Cl minus ions in the solution. It's a strong acid. It will dissociate 100%. If we have weak acids or weak bases, those will not dissociate completely. Yes, and the other thing with this is that weak acids or bases have weak conjugates. So like I said, strong acids and bases produce inert conjugates. Weak acids and bases produce weak conjugates. Very important. Okay, so when we're looking at acidity, just a couple of things here. So having a greater positive charge, having a higher electronegativity, or and being a larger atom are all some of the criteria that we can use to determine acidity, or what is more acidic. So just use those couple of key points there. Okay, so now if we're looking at this equation right here, we have H2O plus H2O equals, or it goes to H3O plus OH minus. This is an important equation to note. This is the autoionization of water. And from this equation, we produce OH minus, it's the base, H3O plus is the acid, and what we get here that we can, from this equation, is we can derive this KW, which I'm going to explain in a moment, is Ka times Kb equals 14. So K is our dissociation constant. When we talk about this K, it's still products over reactants like we've seen before. However, because we have H2O as liquid, we're not including liquid in our equilibrium dissociation constant, right? Which means that we're just left with the products, which means we're just left with Ka times Kb, which is why Kw equals Ka times Kb. This equals 14. You'll see that throughout. You'll see that in a moment. So you'll see why when we're talking about pH scale. I just wanted to make that note. So the K again is a dissociation constant. If the Ka is bigger than 1, it's a strong acid. If the Ka is less than 1, it is weak. Same with Kb. If it has a Kb larger than 1, it's a strong base. If it's a Kb less than 1, it's a weak base. Okay? Let's see what else we have. Okay, so if you're comparing, this next equation I'm about to show you is only for when you're comparing conjugate acids and conjugate bases. So if we're comparing conjugates, we can use pKw equals pKa plus pKb equals 14. And I know we've talked about pK before in our first chapter of biochemistry when we're talking about amino acids, right? We're looking at the pK of amino acids to determine if it was going to be protonated or deprotonated at certain pHs. So with this, we can kind of take it a step further And just mathematically, we can recognize these equations of being pKa equals negative log of Ka and pKb equals negative log of Kb. Those are important to know. We don't have a calculator on the MCAT, but that is okay. Pick up these formulas for now, and you'll see when we're talking about practice problems how you can like implement them. Okay, so just take it right now. And then we have also a note here. It says a low pKa means an increase in acidity. And if you don't know what I'm talking about, go back to the biochem video, chapter 1, amino acids, the last half of the video, last part of the video, go through a titration that we're comparing pKa's of the different functional groups on the molecule. So please go watch that if you haven't seen this stuff yet, because that's really the application of this. And I drew it out. I drew it out and showed you on the molecule what it means to be protonated, deprotonated out of pKa. So that this rest of this will make way more sense if you have seen that video. Okay, so next we can also, because Ka, Kb can kind of be confusing, we can also use pH and pOH. So pH plus pOH equals 14. So what that means, again, like we saw with the equations, we can have pH equals the negative log of H plus concentration. pOH equals the negative log of OH minus concentration. If you're using an acid that is diprotic, okay, you're going to have to multiply the concentration by 2. So if we have like H2SO4, that means that it's diprotic, right? Because there's H2, there's 2 hydrogens there. That means we would have to multiply the concentration that we're given by 2, because it is diprotic. Okay, so these equations can be used if we're looking at strong acids and bases. Simple equation. But if we're talking about weak acids and bases, you need to approach the problem differently. When I'm talking about problems, I'm talking about if it gives you the Ka's and it's asking for the pKa's, if you're given the H plus and they're asking for the pOH, or just so many variations that we're going to talk about in a second. But when I'm referring to those things, I'm just talking about in general with different problems. These equations, right? So just keep them in your toolbox right now until you can really explore when and how to use them. But for weak acids and weak bases, the equation is as follows. So pH for weak acids equals negative 1/2 times log of the Ka times the concentration of the weak acid. Okay, and then for a weak base, it's pOH equals a negative 1/2 log of Kb times the concentration of the weak base. Okay, when we're solving problems with weak acids, weak bases, you're gonna have to use an ice table. Okay, and this is a time where I would say go look up acid base ice table practice problems, because there are so many, and they'll take you through the problems and show you like how to use this equation along with others to really interpret what the question is asking. And like I said, to me, just to speak on it in generalized terms isn't going to be helpful. So like, please just pause it here, or after this video, like I said, just take these things in your toolbox right now and then go to search ice table acid base practice problems, and you'll see what I'm talking about. But what I can tell you is just a quick trick here. So we have, if you're given the H plus, the OH minus, the Ka, or the Kb to be, let's say it's 1.0 times 10 to the negative 1, it could be any of those things, okay? And you're trying to find the pH, the pOH, the pK, or the pKb. What you're going to do, and again, this isn't going to be just magically your answer, but this is just helping with your like conversion to these things based on the equations that you might want to use. This is just like a simple math trick. So if we have a 1.0 times 10 to the negative 1, right? And if we say that is our H plus concentration, if we want to find what the pH of that is, we would take our exponent change the sign and bring it down. So if we had a H plus concentration of pH, our H plus concentration of 1.0 times 10 to the negative 1, our pH is just going to be 1. If we had an OH concentration of 1.0 times 10 to the 8, then that means that we're going to change the exponent and bring it down, so our pH would be negative 8. Wait, did I say H plus? I hope I said H plus for this. If I said OH minus and this was a concentration, then this would be your POH. I can't remember what I just said, but you get the idea. If we have, now this is tricky, we could do this because this number here was 1, but if that number is not 1, you're going to have to employ this other kind of trick. So if we have a number that is not 1, this is a little confusing, so let me just explain it. You're going to have to take the exponent, still bring it down and change the sign, but you're going to subtract 1. So the exponent here, negative 3. So bring it down and change the sign, so we're making that 3 minus 1, okay? Decimal point, 10 minus whatever this number coefficient is in front that you're rounding it to. So the minus 1 point and then 10 minus is going to be the same. The thing that's changing is this and this. So this is your exponent, right? So you brought this down. This is going to be your first thing, is your exponent. Then you're going to take the 6.4, round it to 6. And so your answer is going to be 3 minus 1, which is 2. So it's going to be 2 point, and then 10 minus 6, which is 4. So it's going to be 2.4 is your answer for that. I'm going to do one more problem to kind of show you. So if you have your H plus concentration is 2.1 times 10 to the negative 8. Oh no, it's not just a 1. What do? You can set it up like that. You can do blank minus 1 point 10 minus blank. So you're going to take this, your exponent, right? You're going to make that into an 8. Then you're going to take this number, round it to 2, and put that 2 in there. So your answer is going to be 8 minus 1 point 10 minus 2. So 8 minus 1 is 7 point 10 minus 2 is 8. So your answer is 7.8. So definitely recognize that formula. That will help you with the, kind of conversions if it's just a simple problem, or if you need to use this to put it into another equation. But that is kind of the gist of that. Just a couple more quick things that we're going to talk about in this video, and then we will be good to go. And you'll have all the tools that you need in your toolbox. Okay, so we have 2 other vocab words that we kind of start using in this chapter that are important. So we have an equivalent. An equivalent is 1 mole of species. So if, for example, you have H2SO4, will produce 2H plus, okay, and SO4. You're going to look at this and say this is 1 equivalent of H2SO4 because there's only a 1, right? Theoretically, a 1 in front of this. But it's producing 2 equivalents of H plus and 1, I didn't have space, and 1 equivalent of the SO4 part. But the important part here is recognizing that this mole coefficient is actually telling you also the number of equivalents. So this would be 2 equivalents of H plus. Normality is telling you the equivalents per liter. Okay? Finally, we have titrations. Okay? We have a titrant, which is when you have the known concentration, and then and a known volume, and then titrand is the unknown concentration, but of which you is what you know the volume of, but you don't know the concentration. That's what you're trying to find. So this is a titration curve, and I just drew it very briefly to show you. So this is a pH, so the volume there. So if we're looking at an equivalence point, the equivalence point is the steepest part of your graph. It's a little blurry, I don't know why. It's the steepest point on your graph. Maybe I should wipe this. Sorry. Hopefully that helps. Okay, steepest point on the graph, the equivalence point, and this is where the acid equivalent equals the base equivalent. So if we have a strong acid and a strong base, the equivalence point will be at pH equals 7, so that is neutral. If you have a weak acid and a strong base, the equivalence point is going to be at a pH greater than 7, right? Because you have your strong base, which is kind of carrying more of the weight, I like to look at it that way, which means your pH is going to be greater than 7. It's going to be in the basic range. Whereas if you have a strong acid and a weak base, the equivalence point, the pH will be less than 7. And again, because you have a strong acid, so it's the acid that's be able to dissociate more, that will be carrying most of the weight, not literally, but figuratively, in the pH department. Then if you have a weak acid and a weak base, and you're titrating them, the equivalence point can be above or below 7, and it's just dependent. Then you also have a PI, the isoelectric point, where the pH equals a pKa, and that is this point right here and this point right here. And we see that again, as I said in the biochem video, the first one that I did. We talk about PIs and pKs in more detail with an example. And then finally we have indicators that are going to be weak acids or weak bases, and they're going to display the colors that are dependent on the protonation. So you'll be able to tell if the species has been protonated or not, and it will change color based on that. And that also ties into our end point, and that is when the indicator has reached the final color in our titration. So just because you're adding more of the titrant does not mean that you're going to change color anymore. It's at its end point, it can't take anymore. Another important concept when we're talking about titrations is buffers, and buffers basically just resist the change in pH. Okay, so I know that was a lot, but use this as one of your resources. Please make sure you look at ice tables, because a huge part of this is really applying it right in these different problems. But also, say, okay, I know what a weak acid is now, I know what a weak base is now, like where does this all come into play in understanding the amazing content of acids and bases. So keep studying, you've got this. I hope you have an amazing day wherever you are, and leave your comments or questions below, and I will see you in the next video.